For the new ones, the Meetup is a monthly event we have. We've been doing it for 6 years now. It's meant to be an open space for the data community to learn and share experience involving AI, machine learning, and data science mostly. For those who don't know me, I'm Matheus Facuri. I'm an economist and data science here at Nubank, and I'll be the host of the event today. So today we have a very special meetup. Is a topic that is very dear to my heart. We're going to talk about causal inference today. And for that, we brought in two very special guests. We have Nick Huntington-Klein, who's the assistant professor of economics at Seattle University. He's also the author of the bestseller, The Effect, where he introduces causal inference method in a very accessible and clear way. You should definitely check that out. The book is free, but I think it's out also if you want to buy it on Amazon. Nick also has created lots of other resources to make causal inference more tangible. The one I particularly like was one where he made a bunch of GIFs where he animated lots of causal inference methods and concepts. I've used those a lot in my slides whenever I have to explain some very complicated and counterintuitive causal inference method. I find them to make everything much more tangible, especially the counterintuitive stuff. So thank you very much, Nick. We'll start with Nick's talk on causal inference and identification. Nick, please feel forward. The stage is yours. Thank you.
Well, thank you very much for that introduction. Wonderful. I'm very happy to be here. This is exciting to it. So what I'm going to talk about today is the whole concept of identification. So what are we trying to do, right? So I'm coming to you to talk about causal inference. And first of all, we want to know, what does that mean? And what is the actual difference between what you might typically do in any sort of data analysis and what somebody's going to try to do when they're trying to make some sort of causal claim? So, it's important to ask ourselves, before you do any sort of analysis, what are we using data for, right? What's the reason why we have some sort of data at hand? Why are we all getting paid to do this work? If we're getting paid, hopefully we are. And there must be some point. There's a reason why we're using data, and there must be something that we're going to get out of it. And a lot of the time, in general, the reason why we would use data to answer some sort of question is because we think that the data that we have is to some degree reflective of the world or some sort of system in the world. We think that there's some sort of truth out there, and it is reflected to some degree in the data that we have, right? So if we have like a database full of the cat and dog pictures, and we're trying to train some sort of algorithm to separate out the cats from the dogs, well, why are you bothering to build that algorithm in the first place? Well, because you think that those pictures that you have are reflective of actual cats and dogs that you might want an algorithm to distinguish in the real world. Or even you just think it's reflective of pictures of cats and dogs if you want your algorithm to, go through Google images of new pictures and sort them into cats or dogs, right? We think that there's something in our data that is reflective of some sort of broader thing that we are actually interested in. And the reason why we might use data then to learn about the world is that we are hoping that by analyzing that data, we can answer some sort of question that we have, right? And this should all be pretty straightforward, right? This shouldn't be a surprise, right? If we have some sort of intent behind what we're doing, we're not just throwing things at the wall, right? We have a goal in mind that we're trying to achieve. And so that's our goal, right? That's the reason why we're working with data, because we think that we have our data that's reflective of what the real world is like, and we want to answer questions about what the real world is like. And a lot of data science and machine learning is focused on answering questions about what. These are looking at the data, seeing what sorts of patterns are in the data, and answering questions about that. So, what kind of animal is in a picture? Or, if you're looking at a database of your consumers, you might ask, okay, what are the characteristics of a consumer who spends a lot? When a new customer comes in, and they came from this website and they've done these things before and looks like they have this sort of cookie, can I predict whether they're going to be a really good customer? If I'm building some sort of language processing tool, right? What set of words do I put in what order to address the customer's question? If I want to, forecast, I want to forecast what number of visitors are going to be at my site in the next month. And these are all questions about the patterns that are in the data. I look at the data, and it doesn't really matter why the patterns are in the data. It just matters that they're there and that I can use them to make some sort of inference about new data, right? I have my data set, my database of animal pictures. I train a model on it. I get a new picture. I can get some sort of idea of what kind of animal is in that picture. And so data science is focused on answering these sorts of questions, right? Generally. However, that's not the only kinds of questions that we might be interested in using data to answer. And a lot of these you can sort of categorize as sort of why questions as opposed to what questions, right? These are questions that are not so much about what patterns you see in the data, but rather why you see those patterns, right? These are why questions. So, maybe the question that we're interested in when we're looking at our consumers is not so much can we predict which consumers are going to be great, but the question that we actually want to know is, should we do more advertising? So we look at the data, we observe that there is a pattern in the data that right after we advertise, our sales tend to go up. But why is that? Was it actually the fault of the advertising or the responsibility of the advertising that did that? Or did it just tend to happen, right? Well, we see a pattern in the data. Why is that pattern in the data? Maybe we're trying to train our algorithm to recognize cats and dogs, but what we really want to know is what are the features of a cat and dog that make a person think that it's a cat or a dog, right? So that's a why question as well. We maybe have a chain of swimming pools that we're interested in. We notice that ice cream is a very popular snack, but why is ice cream a popular snack? Maybe your website traffic's been going down. Why has it been going down? These are all why questions that we are probably interested in answering in some way. But you can already see, just by looking at patterns in the data are not going to actually be able to answer these questions to the degree that we want. Maybe not. So these why questions are really important because they don't just tell us about what's in the data. They tell us about counterfactuals and causality. So causal relationships between different things. So going back to the advertising example, maybe I observe that I run some ads in early December. And then I get great sales in late December. So I do see a pattern in the data that my advertisements are followed by much better sales. But the real question that we're interested in is not, are these two things related to each other? Or is there a pattern in the data, which there is? But rather we want to know, should we do more ads? Maybe our ads are particularly awful. They don't actually do anything. It just so happens that we advertised right before Christmas and then Christmas hit and we got a lot of good sales, right? And so anytime you want to understand how things actually work, or often this is the case that we're really interested in, anticipating how a system will respond to a change, especially an intentional change, you want to know why. If you want to know what's going to happen if we buy more ads, then just looking in the data at what the relationship has historically been between your ads and your sales is not going to answer that question. So these are some pictures that you might have seen before, maybe not. But the distinction between these two things, between asking what questions and asking why questions, is very similar to other kinds of problems that you might see of getting weird results in AI, right? So the same problem that we had of if we can see this pattern in the data that our advertisements tend to be followed by sales, even though the ads might not be to get a computer program that could teach itself how to walk quickly, right? So it's a little system. The computer can build itself up a little robot machine, and then it has to walk from A to B. That's all that it was told to do. And so what did it do? Well, it knew that its goal was to get from point A to point B as quickly as possible. So it learned to just build itself up really tall and then fall over. And you could very quickly get from point A to point B without doing much of anything at all. All of our statistical algorithms and methods work in the same way. They have a goal and they will do whatever they can to achieve that goal, often in a sense of improving predictive power. But they don't know why you're asking it the questions that you're asking. So if you look at your relationship between your advertisements and your sales, it doesn't know that your real question is why do advertisements seem to be followed by sales? They just give you the response that, yeah, these two things seem to be related to each other. If I want to predict sales, I can use advertising to do it. That pattern is in the data, even if it's not the one that we are actually interested in. So this brings us to the idea of identification. So nothing that I've told you so far is probably that surprising. You've all heard the phrase, correlation is not the same as causation, right? So we all know that we can't just get a what pattern in the data and expect it to answer a why question of interest. We know that these two things are not the same. We know that correlation isn't causation. However, here's where identification comes in. Saying that correlation isn't causation is a bit too strong of a statement because some correlations are causal. Some correlations do reflect an actual causal relationship between two variables. So for example, if you look in the data and you look at cigarette smoking and you look at lung cancer rates, you will find that those two things are correlated in the data. People who smoke are more likely to have lung cancer. And this is a correlation, and it is also a causal effect. The reason why these two things are correlated with each other is because smoking causes lung cancer, increases the rate of lung cancer in a causal way. So we know that you can't just look at a correlation and say that it's causal. But we also know that sometimes correlations are causal. So how can we distinguish what's going on there? Identification, causal identification is the process of figuring out which correlations are causal. Or more broadly, what calculation or pattern can you actually see in the data? And how do you know when that pattern that you see in the data answers the question that you are interested in and not accidentally answering a different question? Right? If we look in the data at the advertising and the sales, and if we look at the correlation, we say, oh, it looks like advertising tends to be followed by higher sales. If we think that that is answering the question of will advertising improve our sales, then you'd be wrong. You'd have made an identification error. But figuring out how can we do a different calculation that does tell us how advertising affects our sales, that is the process of identification. So this idea is more intuitive than it seems, right? I put a fancy word, identification, on this concept, but this is something that you're probably already doing without knowing it. Although thinking a bit more carefully about how you're doing it will probably make you better at doing it. So if you've ever run an experiment, you've ever done one of those A/B tests, right? Then you have done a form of causal identification. Why did you bother running an experiment in the first place as opposed to just looking at some data? Well, because you probably had a sense that it would make it very easy to identify the answer to the question that you're interested in, right? If we change the color of the submit button on our website, will that cause our click-through rate to rise, right? And okay, well, if we just had a period of time where our submit button was one color and we had a different period of time where it was a different color and we compared them, that you'd know that there's something not really comparable about that. That wouldn't really answer your question. It wouldn't pin down just the explanation that you're interested in. And so you ran an experiment, right? You randomly assign people to get one color or the other. And the reason you do this is because you know that this allows you to actually answer your question of interest. Other forms of identification that we do without even realizing what we're doing, if you've ever adjusted a time series for seasonality, that is a form of identification, right? Going back to our advertising example, we observe that in December, we tend to have more advertisements and more sales. But maybe that's just a seasonal thing. We tend to have more of those things in December than in other months of the year. So we observe a seasonal relationship. We'd say to ourselves, okay, now wait a minute. If I want to know the effect of advertising on sales, I need to account for the fact that, just those two things tend to happen at the same time. So I'm going to account for seasonality. I'm going to subtract out whatever seasonal pattern I tend to see. That is a form of identification. You are taking the pattern that you see and you're thinking, this raw pattern that I have does not actually answer my question. I need to take out some sort of alternate reason why these two things might be related to each other to pin down the explanation that I'm interested in. A lot of the other times, just basic comparisons that you might do are done in the service of identification. Let's say you have a chain of stores. You got some new kiosks in some of your stores. You want to know if they reduce wait times. Well, how would you do this? Well, you wouldn't just look at what your wait times are now. You would want to compare those wait times to some idea of what you think they might have been if you hadn't gotten the new kiosks. So you maybe compare them to other stores that didn't get the kiosks. You compare them to what the wait times were before. Those are all ways of trying to pin down just the variation that has the answer to your question and not something else. So I'm going to go walk through a study that does this. And this is not a particularly business-oriented study, but I think that it's useful because it allows us to walk through this concept of identification and how we can do it in a very methods-agnostic way, right? This is not going to be, I'm not going to give you a big old econometric model or anything like that. It's really isolating the idea of how can we look at just the parts of the data that answer our question of interest without getting distracted by other stuff. So this is a study by Carolina Arteaga called The Effect of Human Capital on Earnings. So the question that she has is, do skills from college courses actually translate into value among new hires? You can imagine asking that question as maybe a recruitment officer in a company, right? So maybe you're recruiting for a data science position, and you're trying to think, well, how much should we really pay attention to, the classes that they took in college as opposed to maybe training on the job? Do they actually learn job relevant skills in college in these data science courses? I don't know. Let's try to figure something like that out. And so you can look in the data and you can observe the relationship between, let's say, taking those sorts of classes in college and job market success. But that's just the stuff that's the pattern that we see in the data. That's the what question. Are these classes, taking these classes, related to job market success? Yes. Yes, they are. Does that answer our question of, did these classes actually make them better workers? That doesn't, there's a disconnect there. There's a couple different reasons why we might see a relationship between the courses and the job market success, other than the one that we're interested in. But we want to pin down that one. We need to identify this effect. So there's a bunch of different reasons why we might think that these two things might be related to each other. Maybe just more skilled people in general are the ones who choose to take the courses. Maybe you are really skilled, but getting an A in your data algorithm or data structures class shows off that you had those skills in the first place, makes it easier to get a job. Different reasons. So how can we pin down just the part that we want? So she thinks about this and she thinks, okay, well, if I want to pin down, if I want to isolate just the answer to the question that I'm interested in, I want to get rid of the part of the data that I see. I want to get rid of some parts of the pattern, because some parts of the pattern that I see aren't related to my question. Some of those parts might be if just differently skilled students tend to make different choices. Some parts might be that, if employers are sort of rewarding some sort of prestige thing, then that's not really related to skill. So I need to get rid of both of those things. How can I find some variation that is not related to both of those things? So she wants to look for some variation in course taking that is not observed by employers, right? So she wants to cut out the part of the explanation, the part of the relationship, the part of the pattern that is just due to showing off your skills. She also wants to cut off the fact that different kinds of people choose different kinds of classes. Well, if we can get rid of that, then we are sort of down to just the explanation that we want, right? We want to pin down just that explanation. So what does she do? She finds a top Colombian business school that happened to remove some classes from its list of course requirements. This was done in a way that employers couldn't really see. So in this case, class taking changed. These students did not any longer take the classes that you might expect would improve their skills, but not in a way that would really affect the prestige of the degree that they were getting. So she has been able to take out the part of the explanation that she didn't want. She's getting closer to identifying just the explanation that she wants. She also needs to take into account the fact that different kinds of students make different choices. So she makes a comparison of the same program before and after the change went into effect, but also too quickly for anybody to change which program they would have entered into. So you're comparing students of similar kinds of skill level. So she's comparing students just before and after the change. She's looking at a change that was not really observable. So you might imagine in this data, the variation that we still see, if we still see a relationship between taking these courses and your job market performance in this data, then that is probably pinning down this idea that these classes actually improved your skills. So what did she find? So this is what she's looking at. And like I mentioned, this is very methods agnostic. This is just literally some averages. Just some means at different points in time. And so what we have here, so this is the college that dropped its requirements. And you can see that the wages that the students who graduated from this program earned were sort of up here, and then they dropped the classes and they dropped, the earnings dropped as well, which we can sort of imagine as being reflective of, yeah, maybe these classes did actually teach students something that made them better at their jobs, able to get a better job. This also suggests another alternative explanation that we need to account for. Maybe just the labor market was changing over time. Maybe the bottom dropped out of the labor market and everyone lost a bunch of money. But it looks like at other colleges, we make that comparison. We don't see that sort of change. So we sort of started with this list of possible explanations, reasons why we see the pattern that we see, and we carved them away one by one until we got to the one that we were actually interested in. If you don't do that process, then there's always going to be a difference between the pattern that you are estimating and the question that you actually want to answer. And so you want to get as close as possible to that. She did the same thing with businesses, this was economics courses, this was business courses. We see less of a change there. Probably could have skipped that slide. Anyway, how do we actually do this? That was my time. All right. How do we actually do this? How can we make sure that the question, the analysis that we're doing, the pattern that we see, the what that we calculate actually answers our question? So we want to, when we look at it, we look at a pattern in the data, we want to ask ourselves in a theoretical sense, why might that pattern be there? What are the reasons why we might see that pattern emerging? That might include the reason that answers our question. In this case, did the classes make them better at their job? But it also includes other stuff that we need to be able to account for. We need to either look for a setting where those other explanations go away. So here in this case, she looked for a setting where something changed about the courses that you were taking in the way that the employers could not see. And in that way, she shaved off one of those explanations. And then she managed to make sort of comparisons that took away other explanations. Maybe the labor market drops over time, just happened to fall apart at the same time the classes went away. But she doesn't see that change in other schools, so that sort of carves off that explanation as well. If you've ever controlled for a variable, that is one way of carving off alternate explanations, right? If you think that, for example, maybe it's the students with the high test scores who are choosing to take these courses, well, you could control for test scores, which you might do in a linear regression sense or a double machine learning sense or whatever it is. We are conditioning on a variable, which is a way of shaving off an explanation. If we condition on a variable, we are removing the part of the relationship that is explained by that variable. So to do this, we can't just rely on the data itself. Everything that I've said about thinking about these alternate explanations and trying to find situations where they don't apply or where we can sort of shave them off, condition for something, you have to think carefully about where you think the data came from, because that's where you're going to get the concept of what are these alternate explanations, so that you can know that you have to get rid of them. You have to figure out what your task is before you can get rid of it. So we have to think about something called the data generating process. This is the set of laws or tendencies that actually made your data exist in the first place. Why do we observe the things that we observe? And this is going to include all those explanations that you need to account for. So to take a very simple example, let's talk about a pen. I have a pen here. And we're going to have two observations in our data set. We have one observation here where I'm holding the pen and you can see that it is up. And then I'm going to let go of the pen and you can see that it is down, right? Those are two observations that we actually have in the data. And the question that we have is why? Why did the pen fall when I let go of it? Okay. And if we have a why kind of question, we need to be able to pin down that explanation. Now we know, because we, are learned people, that it's gravity, right? Gravity is the thing that's making that happen. But what if we had never heard of gravity before, or we had heard of gravity, but we weren't sure that that was actually the reason? And there's a lot of questions where that's the case. There's lots of questions where we look at the data and there's multiple plausible patterns because we don't know which one is right yet. Well, you need to think about what those alternate explanations are. Maybe pens just really love the ground. So when I let go, it goes towards the thing that it loves. Or maybe there's some wind in here that you can't see that is blowing the pen down towards the ground. Or maybe, it's that there's a big old earth down there that's pulling everything towards it based on the squares of its mass or whatever. So knowing what those alternate explanations are so that you can cut them out, maybe if I put a little windshield up here, that would account for the wind explanation. Maybe if we, try to figure out the feelings of a pen, we will find that it does not actually care about the ground, and maybe it's not that it loves the ground. And as you can narrow out those other explanations, you're sort of you're digging out the explanation that you want. And once it can't be anything else, it must be the explanation that you're interested in. In this case, it must be gravity. So one thing that can help in terms of modeling out these data generating processes, something called causal diagrams. This is an idea that comes out of computer science. So it maps on very well to what a lot of data scientists are doing. It's basically a node diagram, right? A graph. If you're into graph theory, you'll recognize a lot of this. So you don't necessarily have to do a bunch of complex mathematical modeling or economic modeling or anything. You just have to ask yourselves what variables are likely to be relevant in this system, right? I have a pen, right? Whether I'm holding the pen or not, that is a relevant variable. Where the pen is, that's the thing that I want to know about. Other relevant variables, maybe the wind, maybe the feelings of the pen, maybe the existence of Earth down there being a very massive thing. These are all variables that are relevant to the situation. Then you just ask yourself, how are these variables going to be related to each other? And if one thing causes another, you put an arrow on that diagram. Once you have this, it's very easy to map out the possible explanations that you have to account for in order to identify your effective interest. continuing on with our advertising and sales example, a very simple causal diagram might look like this. I want to know the effect of advertising on my sales. I put an arrow from advertising to sales because I think that advertising maybe improves my sales. But I need to think about what else might drive my decision to run some advertising. What else might drive the sales that I happen to see? Well, maybe the month of the year. I mentioned the seasonality thing with Christmas. Maybe my recent sales, if my sales are going really poorly, maybe that might be like, oh, I got to shore up those sales. I'm going to run an advertisement. And that is also probably going to be related to my current sales. If sales were bad last month, they're probably likely to be bad this month too. Maybe if I just had a recent product launch, then I'm going to advertise for it, and that'll also affect my sales as well. And so looking at this diagram, you can immediately see the alternate explanations that we might have for why advertising and sales might be related to each other. Yeah, I can walk along this pathway. I can go from advertising to sales. That's the arrow that I'm really interested in. But if I want to know that there's nothing else going on here, I need to make sure that I can't get there any other way. But I can get there other ways. I can go from advertising to recent sales to sales, right? That's a pathway on this diagram from advertising to sales. So I know if I want to pin down just the advertising to sales part, I need to block out the recent sales thing. So I need to make sure that I'm doing some sort of comparison in some way to make sure that I'm comparing apples to apples on recent sales. So I'm choosing months that have similar levels of recent sales, or I'm seeing how recent sales predict sales and I'm taking out that prediction to sort of adjust for it. And the same thing applies elsewhere, right? I can go from advertising to month of year to sales. So if I want to look at narrow down to just the advertising to sales effect, I need to account for seasonality. I need to account for recent product launches. I need to think very carefully and think, did I leave anything out of this diagram? That would be another alternate explanation that I would need to account for. And by doing this fairly simple process, you can get yourself a lot of the way there in terms of knowing what are the alternate explanations that you need to account for, what variables do I need to condition on, or make sure that I can find a setting where they don't apply in order to pin down the effect that I'm actually interested in. Once you have your diagram, all the paths that you can walk along from point A to point B are the different reasons why a pattern in the data might emerge. So one of those reasons might be the pathway that you're interested in from advertising to sales, but these alternate pathways are also generating patterns in the data. And if I don't want those to be the reason why I'm seeing something, then I need to pop them out. So you need to decide which paths do correspond to your question and close the rest by controlling for stuff, by finding situations where paths don't exist. This is one reason why experiments are nice, because if I randomize how much advertising I'm doing, then all these alternate pathways, they go away. Because suddenly, if I'm choosing my advertising levels based on random chance, then all these arrows from this other stuff to advertising go away, and I don't have to worry about those alternate pathways anymore. Now, that said, there are just because you can think of a variable as being relevant doesn't mean you necessarily want to adjust for it. There's reasons why some controls are bad. I'm not going to go into the details on that. Check out my book if you want to know more. But I will also point out there's a great tool called Daggity that is a sort of a diagramming tool that you can use to map out what you think your business problem looks like, how you think the data was generated, and it will help you figure out which variables need to be adjusted for, conditioned on, in order to identify just the effect that you're interested in. I will say this is a process that requires you to get comfortable with making assumptions about where your data came from. The real more than any sort of technical barrier, right? The math of figuring this out is not hard. It's really just once you have the diagram, it answers itself for you, right? What these alternate pathways are, what you need to adjust for. The difficult part is being able to put down that diagram in the first place. And you have to be willing to make assumptions about where your data came from. You can't just look for patterns in the data and say, well, that's the pattern. You have to be willing to make a claim about where it came from, which is something that you can't see necessarily. You need to be able to make assumptions about where you think your data came from. And that means knowing a lot about your context. It's much more difficult to do causal inference in a domain that you don't know than it is to do data science in a domain that you don't know. Because it's not just going from one data to another, it's going from one real world setting to another. And there's a lot of context there to understand. So you got to make assumptions to put this all together. Just for getting in the mindset of having a more theory-driven approach where you have an understanding of why things are the way that they are, as opposed to a data-based approach where you're taking all your cues from the data. Some things to keep in mind: your model is always going to be incomplete. There's no way that this is the full data diagram that explains advertising and sales. But you got to think, well, are the things that I've left off really important or not? Or are they just sort of trivia? It's good to share your diagrams and your understanding and your models with others to see if they can spot anything that you've obviously left out. You can refer to the data sometimes to get some tips on what this looks like. If you are, say, worried about an arrow that maybe should be there or not, then you can look at the correlation between those two variables. If it's very low, you might be okay. There might not be anything there. Additionally, if you want to get more into the details of this and the model that you have might have testable implications. So for example, if we look here, this diagram suggests that there's no relationship between product launch and recent sales. Is that true? I can check in the data for that. If I find that those two things are strongly related to each other, then that gives me a clue that I probably left something out of my diagram that's important. You don't have to fly completely blind. I'll also really strongly recommend something called placebo tests. Your model will often imply effects that should be zero. Are they actually zero? Going back to the Arteaga example, there was a particular period of time where those classes were dropped from the program. And we looked at that period of time and we saw that, yes, at that period of time, we saw this drop in earnings. But that also suggests that we shouldn't see that same drop of earnings if we looked at a different time period. So look at a different time period, see if it's zero there. If it's not zero, if it looks like there's a drop in earnings there too, then we probably left something out, right? Because that doesn't line up properly. In the case of advertising, we should find, for example, that the advertising I did this year shouldn't affect my sales last year, right? That would be impossible. If I do the analysis that I'm going to do, but I substitute in last year's sales instead of this year's, and I find an effect, clearly that's not a real effect. I must have done something wrong in my analysis. So there are ways to check on the work that you've done. Continuing on with that placebo test idea, right? So in that Arteaga case, she also thought, well, okay, there should be some things that aren't going to change. Just because I dropped the earnings. Well, I want it to be the case that the quality of the students coming into the program didn't change. And we don't see any changes in the number of students coming in, their high school test scores. Those things don't really seem to change at this red line where the classes were dropped, which is good, right? We shouldn't see that those things change. And in fact, they don't. And these sorts of tests are good at trying to get a sense of how accurate your model might be. So that's the idea. That's the whole idea of identification, right? We see patterns in the data, but there are many reasons why those patterns might occur. We want to pin down just the parts of the patterns that actually answer our question of interest. Doing so requires us to think about the reasons why we see a pattern in the data, and then try to carve away the reasons that we don't think count. And that can be done in a lot of ways. You can find a setting where one of those explanations doesn't apply. You can use conditioning in order to get rid of some of those explanations. You can do certain kinds of comparisons or seasonality adjustments, all sorts of stuff that take away alternate explanations until you're just left with the one that actually answers your question of interest. And when that happens, you have identified the effect. And if you can get that idea in your mind, the actual method by which you do that is a different question entirely. There are lots of methods that are causal inference methods, but they're really just things that, we tend to use a lot in the realm of causal inference. The actual work of causal inference is the process of identification, is the process of figuring out what are the alternate explanations that we need to get rid of, and what part of the data can we look at to get rid of them. So just to put a bunch of keywords on the board so that you can look them up later if you're interested. There's ways to, a condition on different variables, right? There's regression, there's matching, there's double biasing, also known as double machine learning. Although keep in mind for all these, there are variables that you don't want to control for as well. There's also ways to control for things that you can't measure, which is important because a lot of the time when you draw out your diagram, you'll end up with stuff on there that you can't measure, like consumer sentiment, right, might be on there. For that, there's stuff called like fixed effects or differences. There's also, you can just run an experiment, as I mentioned, which is a way of getting rid of a bunch of alternate explanations by making sure the only reason why one variable varies is for random reasons. But there's also other stuff that sort of mimics a random experiment, even when you don't have one, things like instrumental variables or regression discontinuity. All right, that's it. I think we can open it up for, I'm not sure, I don't know when I started exactly. I don't know how much time we have left for questions, but we can open it up.
We have plenty. So you took 25 minutes. So we have plenty of time for questions.
Good.
Okay, so I'm going to choose the questions not democratically. I'm going to pick the ones that I like best. Sorry about that. So the first, yeah. So the first questions are actually two questions, and both of them are very good. The first one that I want to make is, which are the most popular tools, techniques for causal inference actually used in industry? Can you comment on that?
Let's see here. So what are the most popular tools and techniques that are used in industry? So I would say, experiment. So it depends a lot on which industry you're in. So in tech industries and industries that take place largely on the internet, I would say it's probably A/B tests. They're easy to understand. They're easy to tell your boss about, and they work very well. And you have a lot of control over the environment, so you can run A/B tests. Right? It's very easy to run an A/B test on a website or a service or whatever. Right? Outside of that, I would say that probably the ones that are used the most often are ones that there's two main methods that sort of combine comparisons over time with comparisons across settings. Those two methods being difference and differences, and more recently synthetic control, which is very similar in concept anyway, not in terms of how it's applied. But so, for example, at an unnamed large internet retailer, I know that they make comparisons about, say, the performance in particular warehouses based on changes in warehouse policy by comparing how did this warehouse compare before and after the change, and then over that same time period were there changes at other warehouses in similar ways. Right, that sort of very basic comparison, again, very easy to explain to your boss, and a very clean thing. It doesn't have a lot of super high level modeling, but it works pretty well. And you have because people tend to, because it's very easy to understand your context so well internally, you can apply it broadly, right? It applies in a lot of different settings. The other one that tends to get applied a lot is there's a bunch of different tools for actually, no, I guess that's more of an A/B thing. Yeah, I'll skip that. I was going to say any sort of price setting research is inherently about identification, because you want to know, not, as I change the price, how will my sales change? But there's a bunch of different methods for that. So that doesn't really answer your question.
Cool. And on this, the same person asked this, and I think it's a very interesting question, especially for you that have been teaching causal inference, is again, back into the context that I talked earlier, that causal inference is still not widely applied in the industry here in Brazil. Where do you see, let me rephrase the question, I think, to be more clear. How do we do the convincing part in the industry? Like, how do we convince our boss that this causal inference approach is the right way? How do we talk this? How do we explain this? Do you have any tips on communicating the sorts of techniques and problems to non-technical / management audiences?
So what I experience generally when you're talking to an audience who's not familiar with causal inference is to show the failure of the non-causal method. That it is, I think, intuitive to say, present some sort of correlation first and then say, okay, but is this actually answering the question, or is it that our customers changed in this way, or the setting changed in this way, whatever it is, propose what it is that you think is wrong. So this idea of thinking through the alternate explanations of why we see a pattern in the data, doing that, and then presenting what you think is the most harmful one, right? The thing that's going to mess up your results the most, because that's a pretty intuitive thing, right? The whole statistical process of how you handle that is one problem. But the question of, yeah, okay, I understand that, yeah, maybe the correlation is not answering our causal question of interest. That's a very intuitive idea to get across. I'd say that's the most important first step.
Thanks. And a follow-up question. What do you think about machine learning methods about causal inference? I think you mentioned double machine learning. Do you have any general thoughts on those?
Mm-hmm. Yeah, so the machine learning stuff has been, so seeing machine learning come in and do some causal inference stuff has been interesting, because you really get to see these concepts at play, as opposed to sort of, if you go back, I don't know, 20, 30 years, when it was really just the social scientists doing a lot of this stuff outside of experiments anyway. It was just the tools that we were used to, which was linear regression. We're going to run a probe it maybe, right? Whereas a lot of some of the machine learning researchers come in and say, well, here are the tools that we have, and here's how we're going to address this same sort of theoretical question of how you pin down and identify an effect. So this has come out in a couple of different ways. One is taking advantage of the ability of machine learning to work with high dimensional data. So there have been a number of different methods based on lasso or based on booster regression or based on random forests that take a bunch of different predictors. And this idea that we have these alternate explanations that we need to account for. Well, now we can, it's really hard to convince yourself that you've thought of everything, right? But if you have 5,000 variables, it's probably in there, or at least whatever's not in there, is hopefully not that important. And so the way that actually gets implemented is in that double machine learning approach generally, which I mentioned. Now there are some problems with that. As I mentioned, sometimes those approaches will tend to pick up the bad controls that you don't want to control for. So that is a concern in using those methods. But I think that is a very straightforward way that machine learning can uniquely benefit from causal inference. There are some other ways. Machine learning has been very good at estimating individual treatment effects. So not just, what is the effect of advertising on sales generally, but what is the effect of advertising on sales among our this ethnic group and this ethnic group and this ethnic group, and how does it differ across these different ones? And because you can work with those sorts of high dimensional problems, you can get at that much easier. One method that you can use for this is the causal forest, which is basically an extension of the random forest, but instead of doing a prediction problem in each branch, you do roughly, there's variations, but you look for a covariance. And you try to split the tree based on maximizing the difference in the covariance. In doing so, you can get how the effect differs across different groups, which is interesting. And it's something that's much harder to do in traditional methods.
Thanks. I'm going to have a question that kind of a follow-up to what you said on what we use in industry and how you advocated for A/B testing. I'm going to read the question. I'm going to follow from an personal example of mine, which illustrates the problem. So, hello, amazing seminar. Thank you. I faced a situation in A/B testing, which the treatment is a feature that a fraction of the customers see and choose whether to use it or not, sort of intent to treat treatment. The decision of choosing to use or not may be confounded and biased. How can I isolate the impact of the usage of the new feature in my key metrics? So just to give an example, sometimes in the industry, a problem that we have is that we want to know how good a new feature is. We can randomize the user that gets the feature, but the user has to decide to see the feature. Maybe the user doesn't click on the feature, or the feature is there, but the user never chose to use the feature. So if there's obviously a problem there of there's a choice of the user that you can randomize, you can only randomize the intention to treat. Like, what would you suggest in those sort of situations where A/B testing sort of falls short?
Yeah, so that's a great question. I think that probably the way that I would think about it is, and this sort of goes back to old econometrics thinking, that what we're really trying to do is we're trying to take this idea of statistical analysis away from the realm of probability and into the realm of choice. And often that's what we're concerned about, is that, that we're looking at data that can choose what it wants to be, which makes analyzing it much more tricky, right? And so the thing that you want to think about when you're modeling something like that is you really want to get as good of an idea as possible as to what is it that drives that choice, and modeling that choice as accurately as possible. So you would want to think really carefully about, okay, what is it that's going to drive a customer to be in the situation where they're being randomized? What is the selection process? And once you've done that, that becomes this exact same sort of causal inference problem that I was mentioning, right? And it's sort of it's nested within your broader A/B testing problem, right? And being able to model that out and adjust for the things that you think might be causing you alternate explanations allows you to sort of isolate the random part of your data, right? Taking this thing that, okay, you select into seeing the button and then you get randomized to the button, picking out just the random part and being able to account away all the other things. Often in this particular instance, looking at the intent to treat stuff, the classic approach has been with instrumental variables, which is a way of trying to find parts of the selection process that you can claim are random, or at least unrelated to some sort of the outcome that you're interested in. If you can do that, then you can predict and classify being exposed to the treatment using those random sources of variation that you don't think have any sorts of problems with them. And in doing that, you can basically get yourself back to the experimental setting. It scales the experimental effect by that sort of random push, which is one way that you can do this.
Cool, amazing. Lots of questions popping up. I'll have to filter a lot of them. So there's one that it's like appeared a lot, and it's a question about causal graphs, I think. So one of the question is, you can never be sure that you've controlled for anything. Like, so are there any rule of thumbs on building a causal graph, or how worried should you be that you're not controlling for everything if you don't have if you don't have the possibility of randomization? So
yeah, I think
skeptical
it's pretty accurate to say that in any sort of complex social setting, you're never going to control for everything, right? If you're talking about people, there's always going to be something that you're leaving off of the graph, right? And so there's a couple of things and so the question is not, have I accounted for everything? The question is not, have I put everything on the graph? The question is, are the things that I've left off the graph something that I can call not important enough to worry about, right? You're minimizing the problem, you're not making it go away. And so there's a couple of ways you can do that. One is just to think really hard about what it is that you're leaving out. And if everything that you can imagine that you're leaving out is trivial, then you might be okay. And you'll say, yeah, okay, these alternate things that I'm leaving out, they might be biasing me a little bit in some way, but I don't think that's very big. There are also some approaches that you can use called sensitivity analysis that try to ask the question of, okay, there's some stuff that I've left out. I'm going to make some assumptions about how bad of a problem I think that is, and that will give me a range of possible effects. So for example, I want to know the effect of my advertising on my sales, going back to that one. And I don't control for anything. I think, I know that seasonality is out there. I want to know, but maybe for whatever reason, I can't control for it. And I want to know how bad of a problem that's going to be. And so I can make a set of assumptions. I think that the relationship between seasonality and my choice to advertise is somewhere in this range. I think that the relationship between my seasonality and my sales is somewhere in this range. And from that, I can get a range of how effective I think my advertising is. And this is the process. This is one approach to what's called partial identification, where you're not able to make all the assumptions necessary to pin down one answer, but you can make some assumptions to pin down a range of answers. There's a couple, Celine and Hazlitt have a good paper on this, how to do this, at least in a regression context. Off the top of my head, I don't know a lot of good machine learning partial identification approaches, but that would be very interesting to learn about.
Let me just jump in. We're planning to do a second event on causal inference because this one was very successful. And I'm planning to bring Carlos Sinelli, which is a Brazilian that worked with Julia Pearl, and he's done work with precisely sensitivity. So for folks willing to learn more about this, stay tuned to our following event. I think we have time for one last question. And it is like, what are you most interested about in causal inference these days? Like, what do you see for the future of the area and what you're working on?
I think the areas that I think are most interesting moving right now in development right now is one. I should mention both of them. One of them is is partial identification. That there's a lot of settings where we just are interested in getting an answer, but there's no way that we can possibly pin down that we've gotten all the alternate explanations, right? And so getting much better at figuring out what the range of answers is, the plausible range of answers, I think is going to be a big step forward once that becomes more standard and easier to do as well. So I think that's one thing. I think the other is looking at these heterogeneous treatment effects, looking at how causal effects vary across groups. And this is, again, something that machine learning has made a lot. I mean, it's not new to machine learning, right? We've had Bayesian hierarchical modeling for ages and things like that. But it's something that machine learning makes a lot easier to do and is very powerful at doing. And you get to answer, I mean, if you've ever heard like personalized medicine, right? That's something that this sort of approach would make much stronger. The ability to ask, hey, exactly who is this policy best for? Or most effective on, or exactly who responds the most strongly to this advertising, to keep using that example. I think that those are two things moving forward that are, in a more immediate sense, going to see a lot of development in a good way.
Cool. I think that's it for now. Nick, very happy to have you. Thanks so much for being generous with your time, and feel free to plug your book. Feel free to say whatever where people can find you.
The Effect, you can find it at theeffectbook.net. That's effect with an E, theeffectbook.net. You can read it for free there. You can also, there's also links to buy it. Yeah, you can see me on Twitter as well at NickCHK. I post a lot of causal inference stuff there. I have a pinned thread that has all my projects, including the animations that Matthias mentioned at the beginning. So,
well, thanks a lot again.
Thank you.